Welcome to successive ionization energies and their patterns. Many elements need to lose electrons to become stable, but electrons are held to the atom by the attractive force of the nucleus. Positive and negative charges attract each other, so energy is required to remove an electron from that attractive force. That energy is called ionization energy, or IE, because removing an electron creates a charged atom, which is called an ion. The unit for ionization energy is kilojoules per mole, which refers to the amount of energy required to remove 1 mole of electrons from 1 mole of atoms. Given this definition, does the unit kilojoules per mole make sense? Let's begin by taking a look at energies required to remove electrons from magnesium. The electron configuration is shown at top right, and we are keeping track of the ionization energy in the graph at bottom right. And we see that neutral magnesium has 12 protons and 12 electrons. Note that magnesium wants to lose its 2 valence electrons to acquire the stable electron configuration of neon. The first ionization energy is relatively low, as shown on the graph. Now, however, with 1 less electron, there is more attractive force per electron from the same 12 protons. How will that change the amount of energy needed to remove the second electron? Got it. Yes, you're right. It is harder to remove the second electron. It requires more energy. Notice that magnesium is now a 2+ ion and has reached a stable neon configuration, with even more attractive force per electron. But other relevant changes have occurred as well. Shielding is greatly reduced from 10 to 2, so effective nuclear attraction, or ZEF, significantly increases the attractive force on the current outer electrons. And it has reached a stable noble gas configuration. What will all of that do to the amount of energy required to remove the third electron? Got it. Yes, that's right. It takes a lot more energy. These are called successive ionization energies. The first ionization energy, or first IE, is the energy required to remove the first electron. The second IE is the energy required to remove the second electron, and so on. So these are successive ionization energies, or successive IEs. What patterns can we see when looking at successive ionization energies in adjacent elements? Let's compare the successive IEs of sodium, magnesium, aluminum, and silicon. First, and very importantly, we need to make sure we are acquainted with where valence and core electrons are on our atomic model. It is the outer energy level where the valence electrons are, and it is the inner energy levels where the core or inner electrons are. Note that with these 4 elements, the core electrons represent the stable noble gas configuration of neon. Also important, notice that each succeeding element has 1 more proton, which increases the attraction the nucleus has for their electrons. And now we can compare their successive ionization energies. Let's keep track of each successive ionization energy on a vertical axis at left. The first ionization energy of sodium is low, but that gets us to a neon configuration. So will there be a large change with the second IE? Yes. Sodium's second ionization energy is nearly 10 times that of its first IE. How does that compare with magnesium? We know the first and second ionization energies are low, but the third, now removing an electron from a neon configuration, is much higher. Can you see what the pattern will be with aluminum and silicon? What will happen to their ionization energies once they have lost enough electrons to get to a noble gas electron configuration? For aluminum, the first, second, and third IEs are relatively low. Those 3 ionization energies have removed all the valence electrons. The fourth IE removes an electron from the core electrons, a neon configuration requiring a big jump in energy. For silicon, we see a similar pattern. Now removing the fourth valence electron gets us to a neon configuration. What's going to happen with the fifth ionization energy? You're right! A big jump for the fifth ionization energy, which takes from a noble gas electron configuration. If we compare the successive ionization energies in a table with ionization energies for valence electrons in yellow and core ionization energies in orange, we can see the big jumps in ionization energies for each element occurs at the point when removing an electron from a noble gas electron configuration. Sodium loses one valence electron to get to the 10 electrons of the neon configuration, so there is a big jump at the second IE. Magnesium loses 2 electrons to become stable, so the big jump is at the third IE. Aluminum loses 3 electrons to have a neon configuration, and so the big jump is at the fourth IE. And silicon loses 4 electrons to get to the core, and so its big jump is at the fifth ionization energy. What do you think the pattern would be for elements in other periods? Notice that the amount of electrons removed before a large change in ionization energy is simply equal to the number of valence electrons for that element, and so identifies the group of that element. Elements with 1 electron removed before a large ionization energy change all have 1 valence electron and so are in group 1. Elements with 2 electrons removed before a large ionization energy change all have 2 valence electrons, and so on. You should be able to determine where the large ionization energy change will occur for any element in groups 1, 2, and 13 through 18 based on their number of valence electrons. Note that we have only dealt with ionization energies of main group or representative elements. Because transition metals are filling d orbitals and can lose more than one specific amount of electrons to become stable, their successive IE patterns are more obscure. That's it for today's Mad Scientist production. See ya.